Welcome to the presentation, Cybersecurity for Euro, Task 3.3 SDL Software Development Lifecycle. Supporting the security by design within the SDLC. Semco consists of a methodology for the creation of a design and analysis framework for handling the composition and integration of architecture and security that semi-automatically supports the analysis of architecture and its security. In the context of our experiment, 1. We use component port connector and message passing communication to specify the software architecture of distributed systems. 2. The security requirements are specified in terms of threats as properties on the system model using the STRIDE classification. 3. The security architecture of the system is then evaluated accordingly. 4. Security policies can then be introduced to stop or mitigate them. The approach associates model-driven engineering, MDE, and formal techniques to design a set of modeling languages for specifying and analyzing architecture and property models, which allows reuse of capitalized security-related know-how. The tool suite. We have implemented an MDE-based prototype connected to a tooled formal language, Alloy, to support the proposed approach. An example of this tool suite is constructed using EMFT, Xtext, and Xtend, and is currently provided in the form of Eclipse plugins. The architecture of the tool, as shown in the following figure, is composed of two main blocks. 1. Modeling framework block providing DSL and formal languages, model transformation engines, and reusable formal models. And 2. Application development block dedicated to the architect to model and analyze the security architecture model of a concrete application. Smart Cities Reference Architecture. We use a smart city systems to illustrate the proposed approach. A smart city can be seen as a distributed data lake of information where multiple devices collect and store data ready to be queried by external parties. A high-level architecture for smart cities is visualized in the figure. For instance, information are collected from devices, sensor components, acting as sensors and/or third-party systems through data collector components. Data lake are managed through data management and data store components, where information are transformed to data according to the targeted applications. The resulting data are then provided for consumption directly by application and/or service providers. Smart Cities Security Architecture Requirements. In this study, we only focus on the protection of the collected data asset. This asset faces the following threats: SR1, SR2, SR3, SR4, information disclosure, elevation of privilege, spoofing, tampering, comparable to a classic information system and its security requirements. SR5, need to separate legitimate claims from false claims made by system components. And SR6, loss of data during communication hinders proper operation. DSL and formal models. After setting up the design and analysis tool support framework, including the conceptual and development phases, providing a set of modeling and formal languages and formal model libraries for reuse. Smart Cities Architecture Modeling and Threat Specification for Detection. 1. We start by defining the component types, the ports and connectors using the DSL software architecture model. 2. Then we specify the potential threats on the architecture model by using the STRIDE model library. For instance, SR1, SR3, SR4, SR6 on the connector linking the data collector component to the data management components, and SR2 and SR5 on the data management component. Alloy model generation for analysis. Counterexample for threat detection. 3. The next step is to generate the corresponding alloy architecture model integrating automatically the specified threads using the already defined formal model libraries. Alloy analysis. Counterexamples and report generation. 4. Then the architect proceeds by invoking the alloy analyzer to find issues, generate counterexamples, and threat analysis reports. Smart cities architecture modeling and policy specification for treatment. 5. Then the architect revisits the DSL model, incorporating a set of previously developed DSL security policy libraries with the help of the generated threat report that suggests adequate security policies associated with the identified threats, example, spoof-proof, in order to mitigate them. Alloy model generation for analysis, threat, and policies. 6. The resulting DSL model is then transformed to a formal alloy model, where the formal definition of the corresponding security policies are automatically added in the produced alloy software architecture model from the DSL definitions. Policies report generation. 7. The alloy analyzer is then invoked with several iterations to detect the targeted threat. At the end of the mitigation, that is, when no counterexample was found when the alloy analyzer is invoked, the security policies report is generated as an HTML document as visualized in the figure.